Okay, so we're going to be going over heap sort. So what is heap sort? It's a sorting algorithm. And it's used to sort the binary heap data structure. Um, and the way it sorts is by finding the top element of a heap and swapping it with the last element in the array. You'll see what I mean by this later. So we're going to be using min heaps because this is just how my code is, or how the code is. I think max heaps are more common, but it is what it is. So let's take this array 23, 48, 95, 79, 10, 4, and 9. Let's take this array and heap sort it. So first, we're going to write out our array as a tree. Just as a regular tree. Nothing special. Okay, so as you can tell, this is not a proper heap of any sort. So we have to run heapify all. And what this does is it will take our current array and make it into a proper min heap. So what this looks like in array form is 4, 10, 9, 79, 48, 95, and 23. And let me write this out in tree form. So let's start with the sorting. So we find that the smallest item is at the top of our array, and it's 4. So we have to swap this with the last element in our array, which is 23. So we do that. And we remove 4 from the heap. So let me draw this out. So this we have swapped 23 and 4. You remove 4. And now we do not have a proper heap, so we must run heapify, which will fix our partial heap and turn it back into a min heap proper. So So Heapify first looks at the next children. So we have 10 and 9. So Heapify is going to pick 9 as the new top because it's the lowest number out of 10 and 9. And we want the lowest number up top because this is a min heap. Okay, now that looks better. So now, oh, let me move this down. So now we're looking at, oh, I forgot the 4. Oops. So as you can see, we're starting to have like we're starting to have subarrays within our array. So the 4 is the start of the sorted array, sorted subarray, and the rest of them, this part of the subarray, the left part, is are the numbers that are still in the heap that are still trying to be sorted. So let's continue. So our new top is 9. That's our new top. And the last element in our heap is 95. So let's swap these two. Now let's remove 9 from the heap and put it into the sorted part of the array. Now let's call Heapify to turn this back into a proper min heap. So 10 should be the new root. However, 95 is still a bigger parent than 79 or 48. So we will take 48 to be the new root of this of the subtree. And our min heap is happy again. So our array turned into this. And then we turned it into this. I was looking at the wrong one. And this is our heap. That's our heap. So the new top is 10. We're swapping it with 95 yet again. So let's write that out. And then let's remove 10 from the heap. Okay, so yet again, we do not have a proper min heap, so let's fix that. Let's call on heapify. So 23 should be the new root. And this is our new heap, and this is our new array. And this is our heap. So I'll just keep going without the explanation. I think y'all get it by now. Feel free to speed up this part. Okay, so we're at the end of our heap. There's only one number left in the heap, the lonely number 5. So we cannot call heapify again because there's nothing to heap. So this is our final sorted array. Um, and let me show you the code for this. So for heap sort, we have, oh yeah, we're using min heaps in this heap sort, so keep that in mind. You can make a heap sort with max heaps as well. So this is the array that's going to be sorted. This is the last index of the array where there is a valid min heap. So first we call heapify all to turn our initial array into our initial min heap. So this is the loop that does the sorting of the heap. You exit this loop when there's only one element left in the heap, because then there's nothing to be sorted. So the swap function, it swaps the top of the heap and the last index of the array, or the last index of the heap rather. They swap places. And since that swapped element is put outside of the heap because it's already sorted, you decrement the end of the min heap by 1 because the heap has shrunk. Or yeah, you decrement the index that indicates the end. And then you take that your new smaller heap and turn it into a proper min heap again. And you do this so you can keep sorting properly with each iteration. So heapify all, it turns your array into a heap. It takes an array and the end index of where there's a valid min heap. So there's a for loop, and inside heapify all, there's a for loop, and it just calls heapify again and again and again. And what this for loop does is it checks all the parent nodes, and makes sure that their children aren't like greater than them. And it starts like in the middle of the heap, basically, because like you don't really need to care about the leaf nodes because they don't have children. And then we have heapify. This is the second dig method in heap sort. So it takes a partially sorted heap and it turns it into a proper miniature heap or minimum heap. So it takes the array that needs to be sorted and the top, which is the current top of the heap, and the end, which is the last valid entry of the min heap in the array. So min child keeps track of what index of the heap is being looked at, and you keep the loop going so long as there's a left child present. So you exit this while loop when there's only one child left in the heap. We automatically assign the left child as the smallest, and then we check if there's a right child that exists, and we have to check if the left child is greater than the right child. Then that means the right child is the smallest, so we increment this value of min child to reflect that, because as you can see, this is the formula for to find a left child from a root. So if you add one more to that, you get the formula to find a right child. So this would then be assigned to this would then be the index of the right child. If the parent of the child has a bigger value than the child itself, then that's not a proper min heap. And then you have to perform a swap to fix this. And then you have to reassign top to min child because the child has now become the parent. That is a very weird sentence to say. And then you exit the method if there's no more swaps that are necessary. This is a swap method. It's very simple. You just swap the values. It takes an array, which the array that you've been sorting this whole time. the integer I, which is the first element that needs to be swapped, and the integer j, which is the index of the second element that needs to be swapped, and then it swaps them. That's not too difficult. All right. And finally, we have the time complexity. Wonderful. So the time complexity of heap sort. So let's take a look at the methods within heap sort. So we have heapify all. This runs in linear time because it depends on how big the array is. So it depends on like the number of elements in the array. We can call that n. And this therefore means that heapify all runs in O of n time complexity. Now heapify since this is based on the height of the tree of the heap, it is called n minus 1 times, which we can simplify to n because the 1 is negligible. So we have to multiply this n by the height of the heap, which is log n, and we will get the time complexity of O of n log n for heapify, because this is the because we multiply the number of times it's called by the height of it. So once we add this together, we add both operations together. So we have O of n plus O of n log n. But this value is negligible, the heapify all. Compared to this, the n log n is the dominant time complexity. So we can get rid of this, which leaves us with a time complexity of O of n log n for heap sort. And this is true for all the cases. For all the cases, it will be an n log n time complexity. However, there is a best case scenario where all the keys are the same. And O of n, because all the numbers are the same, so heapify just stops immediately. Do you need to know this? I will hope not. I'm just telling this to you just in case. Yeah. That is heap sort. And that's about it. Thank you.